It's coming, yeah.
Okay. I need to get this out.
You're hide. Floating. Yeah, excellent.
All right.
Okay. Yeah.
Thank you so much, Shin, for a wonderful introduction. And thank you all for having me here and giving me the opportunity to share a little bit about my research with all of you. So over the next 20 minutes, I'll tell you about my pursuit for observable signatures of the origins of supermassive black holes and how I do this using large-scale cosmological simulations. So as we all know, what's going on? Okay. As we all know, supermassive black holes exist in pretty much every massive enough galaxy in our universe. And the big question, of course, is what are their overall cosmic origins? Where did they really come from? So these supermassive black holes can weigh anywhere from a few million times the mass of our sun to a few tens of billion times the mass of our sun. And the standard expectation is that they're probably not born at these masses. These are simply too high. So perhaps they started out as much smaller, what we call seed black holes. And then the fundamental questions basically become, how did these seed black holes form? What were the detailed formation mechanisms? What were the initial masses? And finally, how did they grow eventually and become supermassive? So there's a wide range of different hypotheses that have been proposed for the nature of these black hole seeds. These are the three most popular leading contenders, and all of them are presumed to most prevalently occur in the early universe when the gas was largely devoid of metals. So the most natural contender is the remnants of the very first generations of these metal-free, population-free stars, which at the time of their deaths are expected to leave behind remnant black holes, perhaps about 100 solar masses or so. And these are called POP3 seeds or light seeds. And then you can have perhaps somewhat more massive seeds that can come from runaway collisions of stars in dense nuclear star clusters. And these could perhaps leave behind seeds that can range anywhere from maybe 1,000 to maybe 10,000 solar masses. These are also called medium-weighted seeds. And finally, perhaps under rarer circumstances, if you can somehow remove the only other effective coolant in an otherwise metal-free gas, which is molecular hydrogen, then you can come across perhaps a situation where an entire gas cloud can directly, monolithically, and isothermally collapse into a black hole, completely skipping over your standard star formation or stellar evolutionary stages. And in this way, you can form what we call direct collapse black hole seeds. And these are also called heavy seeds because they have been postulated to have masses perhaps ranging from 10,000 solar masses to about 100,000 solar masses. So these are the three most popular, what we call astrophysical channels of seeding with known baryonic physics. And from here on in this talk, I'll just try to simplify this a little bit and lump together these light and medium weighted seeds and just collectively call them low mass seeds and contrast them against these heavy seeds born out of these direct collapse black hole formation conditions. And the standard expectation in terms of their abundances is that these low mass seeds are expected to form much more commonly in the universe compared to these heavy seeds, which are generally canonically by the community has been expected to be exceedingly rare. But as we shall see in a few slides, that perhaps some of these very exciting JWST observations, especially compared against my simulations, may be suggesting that perhaps the universe has much more effective ways to produce these heavy seeds compared to what these direct collapse black hole formation theories suggest. Should we try to fix this or?
Yeah, I think let's see if I can. Trying to see if there's a mouse.
Maybe we can also cancel the recording if you want to fix this. The thing is, I can't. Problem with this screen is I can't see the mouse pointer. They are here somewhere. Oh, there. Let me try to do this.
Extrapolate the path of the
There. No. Spoilers, thank you. I mean, it is, I'm finding it, right? It's getting highlighted, but it's not. Well, should we just cancel the recording?
I can.
It's transcript.
It's a transcript, but I can.
Okay. Sorry.
I think it's a transcript. Yeah.
Oh, I see.
You just get out of presenter mode. Did you get your mouse back? That works for me.
I'm trying to press escape and it's not going.
There we go.
Got it. What I see? Okay.
That's the okay.
Okay, let's see.
Okay.
All right. Oh,
No, wait. The share screen. I'm assuming.
Yeah, and hide.
hide floating media.
Yeah. Okay. Yeah.
Great, thank you. Yeah, now it's distracting. All right, where was I? Yeah, so standard expectation, low mass seeds are extremely common. Heavy seeds, canonically, the community has expected to be forming exceedingly rarely. But as we shall see, that maybe some of these exciting JWST observations might suggest, especially compared to my simulations, they may suggest that the universe has much more effective ways to produce these heavy seeds compared to what we have canonically expected through these direct collapse black hole formation models. So that being said, JWST has really revolutionized this field of not just high redshift galaxies, but also high redshift black holes. And especially at redshifts of 4 to 7, JWST has detected a large populations of these black holes, which were previously completely hidden from our view. And here are some more examples of some of the most distant black holes discovered by JWST, completely shattering previous records of the most distant black holes discovered before them. Objects like GNZ11, Kuiper's LRDZ9, UHZ1, etc. And these have demonstrated that up to about 100 million solar mass black holes could have existed already at as early as redshifts of 9 to 11, which is very extraordinary. So with all these exciting discoveries, JWST has really taken us a huge step forward towards eventually, hopefully, detecting directly these seed black hole populations. And to do that, we have to detect smallest black holes possible at the earliest times. And before JWST, the only black holes that were observable at such early times were these billion solar mass black holes powering these most luminous quasars. And now with JWST, we have started for the first time detecting these fainter AGN populations being driven by smaller mass black holes. And I was going to say we had a very exciting future ahead about a few hours ago, but then I just got the news that Access got cancelled. So unfortunately, that's a setback. But nevertheless, we also have other observatories such as gravitational wave facilities like LISA, which is going to really break past the limits of any previous electromagnetic observatory and perhaps be able to detect down to maybe 10,000 or even 1,000 solar mass black holes as early as redshifts of 15 or so. So with all these exciting prospects, we can really anticipate by the end of the next decade to be able to reveal a huge bulk of this postulated seed black hole population from these different theories. So this makes it an extremely crucial time for us to also continue building our ability to make robust theoretical predictions for these black hole populations, because it is only when we have these predictions that we can confront them with these observations and ultimately reach our key science goal, which is to unravel the nature of the first black hole seeds. So as I mentioned, I generally do this using large-scale cosmological simulations. And over the past 5 years or so, I've spent a considerable amount of time building new approaches to model the formation of these seeds and distinguish between different seed formation channels in these large cosmological simulations. And this has culminated in the creation of this BRAHMA cosmological simulations. BRAHMA basically refers to the god of creation in Hindu mythology. And since these simulations focus on the creation of black hole seeds, I thought it was a very appropriate name. So we reveal a wide range of candidate sites for the formation of these different types of seeds. So here's an example of a birth site where we can expect low mass seeds to form. So I'm basically taking some of my highest resolution BRAHMA simulations and zooming into one of these proto-galaxies and revealing the gas density, the star formation rate, and the gas metallicity profile. And this yellow ring here marks one of these seed formation sites, which you can see where the gas is actively forming stars, but is also simultaneously devoid of metals. And the prevalence of these kinds of situations in our simulations will basically determine how frequently these low mass seeds will form. And here is an example of one of my simulation results, which shows the formation history of these low mass seeds. On the y-axis, I'm showing the number density of new seeds as a function of redshift. And you can see how the first seeds essentially emerge around redshifts of 30, followed by a ramp up of seed formation from redshift 30 to close to redshifts of 12. And all of this is basically driven by the emergence of the first regions of dense star forming gas in a universe which is otherwise prior to that largely metal poor. But of course, eventually these star forming regions will metal pollute the universe. And this will slow down the seed formation. And by the time you get to, in this case, redshifts less than 9 or so, large portions of the simulation box becomes polluted with metals, which eventually puts a stop to our seed formation. We can do a similar exercise by also trying to identify candidate sites where we can place direct collapsed black holes or heavy seeds. And here's again another example of a zoom into another proto-galaxy. You got the density, metallicity, and star formation rate profile. Notice that I've also added a fourth panel over here, which basically shows the intensity of ultraviolet radiation that is exposed to the site, which is to say that these heavy seeds are placed in those pockets where the gas is dense enough to potentially form stars. It is also devoid of metals, but the surrounding star-forming regions around these pockets is able to provide enough ultraviolet radiation that it will block the cooling of the molecular hydrogen, block star formation in the process, and instead create conditions for these formation of these heavy seeds. The prevalence of these kinds of situations will determine how frequently these heavy seeds will form. And here's another example of a box which exclusively focuses on these heavy seed formation. And you can immediately notice that the formation rates for these heavy seeds is, in this case, 4 orders of magnitude smaller than that of these low mass seeds. And this is largely because the requirement of strong ultraviolet radiation to produce these heavy seeds is extremely stringent. And this is also why the community has canonically expected these heavy seeds to be exceedingly rare. But these are just a handful of boxes that I'm currently showing you. But the real strength of the BRAHMA simulations is that we have not just a handful, but really a large ensemble of boxes spanning a wide range of volumes and resolutions between 9 to 72 parsecs or so. And each box has a different flavor of our seed formation model, which is all parameterized into a universal framework. And then we explore the parameter space with these boxes, creating the largest simulation-based systematic study to quantify the impact of seed models on black hole populations across cosmic time. Studies of these kinds have been previously done largely with some analytic models, and Angela Ricarte can tell you a lot more about that. So just to give you a demonstration of that, here you can see a few more boxes showing the immense diversity of the seed formation histories. And then the goal is to try and understand how does this diversity then get translated into different signatures on the supermassive black hole populations that we could observe in the future. So from this point on, I will basically be focusing on showing you some predictions from the BRAHMA simulations for different signatures of black hole seeding relevant for electromagnetic and gravitational wave surveys. And I'll start with predictions relevant for electromagnetic surveys, and I'll walk you through different epochs in our cosmic timeline, starting with the earliest epochs of redshift 9 to 11, where JWST has detected the most distant black holes. And these are the green ring basically encircles these black hole mass measurements. On the y-axis, we got the black hole mass as a function of redshift. And we can compare these measurements to predictions from our simulations now. So here I'm starting with showing you predictions from 2 of my simulations. So for these simulations, we basically track the evolution of the most massive black hole. And you can basically see the blue line basically shows a simulation that assumes a low mass seed starting at 10 to the power 4 solar masses and produces abundant numbers of them. And then the orange line shows a simulation which focuses on heavy seeds starting at 10 to the power 5 solar masses and produces extremely few numbers of them. And generally, you can see both of these simulations tend to struggle to produce even the smallest of these JWST black holes, which again goes to say that the mere existence of such black holes at such early times puts a stringent challenge to any of our standard seed formation scenarios. And in doing our systematic exploration, it turned out that the only models that are able to produce even the smallest of these JWST black holes are those that produces these heaviest 10 to the power 5 solar mass seeds in much more abundant numbers compared to what we have so far canonically expected based on direct collapse black hole formation theories. So, and this is largely because having such high numbers of seeds can drive a lot of early black hole growth from mergers, black hole mergers, and in this case, enough to be able to reproduce at least the smallest amongst these black holes. But even this rather extreme manifestation of seeding cannot reproduce the larger amongst these JWST black holes, objects like UHZ1, GHZ9, etc. And it turns out to be able to produce that, we need an even more extreme scenario where we not only have abundant heavy seeds, but we also have to ensure that they merge very efficiently, assuming very small delay times between the mergers of the galaxies and the subsequent mergers of the black holes themselves. A similar story arises when we go to slightly later redshifts and redshifts of 4 to 7, where JWST has detected the large populations of black holes shown by these black points in terms of the black hole mass versus galaxy stellar mass relation. You can compare them against the local scaling relation, the mean of which is shown by this thick black line. And you can generally see how most of these black points are systematically above the local scaling relations. So we say that these JWST black holes are overmassive, so to speak. And then we can compare them against predictions from a wide range of our different simulations. And you can again see that generally these low mass seeds and heavy seeding channels shown by the blue and orange points tend to be substantially below these JWST measurements. If we switch to a lenient heavy seeding model, then we produce much better overlap, at least at the smallest galaxy masses, shown by these red circles. And finally, if you want to produce a systematically overmassive stellar mass black hole mass relation at these redshifts across the entire range of galaxy masses probed by JWST, then we need, again, not just a lenient heavy seeding model, but also merge them very efficiently within less than 750 million years after their host galaxies merge. So overall, the implications of the JWST measurement can be basically summarized as, in terms of what is hinted by our BRAHMA simulations, we favor much more efficient formation and merger-driven growth of these heavy seeds compared to what we have canonically expected so far. However, I would not put a final verdict on this because there have been other possibilities that have also been put forward by other modelers using other types of modeling tools. For example, there are some semi-analytic models that have suggested that if you assume bursts of extremely rapid super Eddington accretion, then you could produce these JWST black holes without the help of early black hole mergers, simply from gas accretion. Our simulations don't show this kind of super Eddington accretion, but that might also be due to some modeling uncertainties in the simulations, which we are currently exploring. The second possibility is that of these primordial black holes that are proposed to form much earlier than the epoch of galaxy formation, closer to the epoch of recombination. And this would give them a much better head start to grow their masses before the first galaxies even emerge. And then the third possibility is that perhaps we can completely obviate the need to grow these black holes from smaller masses at all by directly producing seeds already in the supermassive regime. And there have been some recent simulations that have suggested that this might be possible under certain circumstances. And the final possibility is from the observational side, where there's a debate amongst the observers about whether these black hole masses are actually overestimated. And this is largely because a lot of the techniques for making these mass measurements, you guys will know better than me, has been largely focused on low redshift black hole populations, and it may not trivially translate to making accurate measurements at high redshifts as well. So we have all these different possibilities, and the question is which one is correct. Well, at least for the scenario that my simulations have tilted towards, which is this abundant heavy seed formation paradigm, I'm going to show some complementary predictions from this paradigm in very different observational regimes. We have 2 minutes? Okay, sorry.
Guy, you have 2 more minutes and then like maybe 3 more minutes.
Okay, so I'll show you some complementary predictions which can then be in the future be either used to validate the scenario or to completely falsify the scenario. So here I'm basically showing you a simulation which focuses on the environments of these brightest quasars that we find at redshift greater than 6. And here, the gray distribution on the left basically shows the dark matter distribution, and then the red points basically show the stellar distributions. And this is basically a 10 to the power 12 solar mass halo at redshift 6, so a very overdense environment. And if you look at the black hole positions, this is basically a prediction from the standard heavy seed formation paradigm, which produces seeds in much more restrictive numbers. Then overall, there's nothing out of the ordinary here. You basically have a black hole at the center of the halo, and it's shining really brightly, consistent with the high redshift quasar population. If you zoom in to the right, you can see a few companion black holes, but they are far from being detectable, so not really super relevant. But now let's look at what happens when you switch from a standard heavy seeding paradigm to a lenient or abundant heavy seeding paradigm. So now, all of a sudden, in these environments, you can see a vast population of these wandering black holes. And even then, if you just think about the detection limits for JWST, then you can basically see only the central quasar is the one that's going to be detectable. So basically, all these wandering black holes are not going to be detectable. But now let's look at if we consider some fainter detection limits that have been proposed for future surveys. So, for example, if we take the sensitivity limit for the planned AXIS mission, then we can see that in the immediate vicinity of the quasar, there are a few AGNs which are falling within the sensitivity limit for AXIS. However, if you look at the zoom in, you can see that the angular resolution of AXIS would not have been nearly enough to be able to individually resolve these AGNs. So that would have been unfortunate. But now if we go even fainter at the proposed sensitivity limit for the LINX mission survey, and now you can see a much wider set of these companion AGNs located a bit further away from the central quasar. That falls within the sensitivity limit for the proposed LINX mission concept. And at the same time, the angular resolution of the LINX mission concept, in this case, I have assumed 0.5 arc seconds, would be enough to at least resolve perhaps a few of these companion AGNs. So I don't know what the current status of LINX is, but maybe if we need a science case to push forward for LINX in the next selection for decadal surveys, then this might be one which could help the case as well. Now, coming all the way to redshift 0, we can also look at occupation fractions of black holes in local dwarf galaxies. And we can see that amongst all these seeding scenarios, the abundant heavy seeding scenario produces the strongest occupation fractions. And I'll basically conclude by showing you one more result after this. And then final result I want to show you is just the rates at which black holes merge at different epochs in our cosmic time in our simulations. And this could be detectable with future LISA. And again, the standard seeding scenarios predict maybe a handful of mergers in terms of their peak merger rates. But the abundant heavy seed formation scenario is the only one that predicts up to 100 mergers per year. So if LISA is able to detect so many mergers per year, then this would strongly support our heavy seeding scenario, making it like really a smoking gun signature. But if we don't detect as many mergers, then it would falsify the scenario, and maybe some of the other scenarios proposed by other modelers would be correct. And with that, I come to the conclusions. Thank you so much, and sorry for the technical difficulties.
Yeah.
Yes, thank you so much, Aklant. Maybe a few questions.
2 questions. So first, then Sean.
Thank you, Aklant. This is great. So, can you go back to the black hole versus stellar mass prediction?
Yeah.
Black hole mass prediction.
Yeah.
Yeah, I was just wondering. So, because when you show the heavy seed with the fission merger,
Yeah.
So, I mean, I find it a bit hard to believe that. I mean, all black holes are extremely romantic, right? Like, I mean, they may be a little bit high and local, but still we are in a tip of the iceberg.
Yeah, actually, so, one of my latest papers, that's what I basically argue. So this is a very extreme manifestation. This is like, I'm not actually arguing that this is actually what's happening, because it is true. Like, probably these black holes are a tip of the iceberg. over a much over an underlying black hole population, which may be consistent or maybe slightly higher than the local scaling relations. We don't know, different people say different things. But this is just one seeding model. And the idea was to show like under what circumstances can you produce overmassive black holes at different galaxy masses. And it turns out that you need lots of mergers or efficient accretion by reducing feedback, but that kind of messes up the low redshift galaxies. So we have all these different ways we can produce them, and some of which can break other stuff. In this particular scenario, it's interesting that even if you produce a very overmassive, this is a pretty extreme seeding model. I'm not actually arguing that this is actually happening in the universe. Maybe it's like slightly less lenient than that, but it is interesting that in this seed model, if you track them all the way to redshift 0, then you can actually produce the local scaling relations. Yeah, that's okay.
Thank you. This is super exciting work, but unfortunately we have to conclude for CfA Live. Thanks for completing this task, even despite the technical issue.
No problem. Thank you.
But Aklant will be sitting in office B431. Please meet with him in the rest of the day if you have more questions in sessions. But thanks both speakers.